Hello. Today in this episode is about a pattern I shipped in production at a media distribution platform. The problem was simple to describe, genuinely hard to solve. Business users need to ask questions about catalog, which titles are underperforming, which genres have highest return rates, how revenue trending by region, and they needed answers in seconds, not in tickets to the data team. The traditional answer is a BI dashboard. Build the dashboard, define the metrics, let users filter and drill down. The problem is that dashboard answers questions you anticipated. They do not answer questions the head of distribution asked 9 in the morning on a Thursday that nobody planned for. Natural language to SQL is the answer to that problem. The user types a question in plain English. The system generates the SQL, runs it against the database, and returns the result with a chart and a summary. In this episode, I am going to build that pipeline using Vanna for query generation, DuckDB for in-process execution, FastAPI for the API layer, and Claude for the summary. I will also cover the two failure modes that matter in production: SQL injection to view LLM and hallucinated column names. This episode 4 of AI Engineering for Real Apps, we have built the multi-agent pipeline, the structured API, and the browser agent. This is the reporting layer. Let us build it. Before I touch any code, I want to show the gap that NL-to-SQL fills and why a BI dashboard is not the right answer. A BI dashboard answers the question you anticipated when you build it. You define the dimensions, you pick the metrics, you set up the filters. The dashboard is a fixed query against the data. The query just has a lot of parameters. When a user asks a question that does not fit the dashboard, they have two options. They open a ticket to the data team, which take days, or they export to Excel and do it themselves, which is produce 5 different spreadsheet versions of the truth and breaks the moment of underlying data changes. NL-to-SQL fills the gap by making the query layer accessible to non-technical users. They type a question, the system generates the SQL, the database runs it, the user gets a result they can act on. But NL-to-SQL has a reputation problem. Earlier approaches were brittle. The model generated synthetically valid SQL that required columns did not exist, or it joined tables in ways that were logically wrong, or it generates SQL that was correctly for a different version of the schema. Vanna solves the training problem. You teach Vanna your schema with DDL and example question to SQL pairs. When a user asks a question, Vanna retrieves the most relevant training examples and uses them as a context for generation. The model is not guessing your schema, it has seen it. Combined with DuckDB for execution and Claude for result summary, this is a complete reporting pipeline. Let me show the full architecture before we go into each component. The architecture has 4 components. First, Vanna. Vanna is an open source NL-to-SQL framework. You train it on your schema, DDL statements, and example questions to SQL pairs, and it generates SQL from natural language questions using retrieval augmented generation. The training examples are stored in a vector index. When a new question arrives, Vanna retrieves the most similar training examples and includes them in the generation prompt. Second, DuckDB. DuckDB is an in-process analytical database. It runs inside your Python process, no server, no connection string, no infrastructure. You load your data as paraquet files or CSV, run SQL against it, and get back a pandas data frame. For reporting use cases where data is refreshed periodically rather than continuously, DuckDB is often the right choice. Third, FastAPI. The API layer is single post endpoint /chat. It receives a natural language question, calls Vanna to generate SQL, execute the SQL against DuckDB, calls Claude to summarize the result, and returns structured response with SQL, the results row, the chart JSON, and the summary. 4. Claude. Claude is not the query engineer. That is Vanna. Claude's role is the last step. Take the results row and produce a plain English summary with a follow-up question, a suggestion. It sees the result, not the query. We do not send the full result set. We send a truncated sample plus the count. It's a bounded context. Let us start with Vanna training because getting the training is what makes everything else work. Vanna training happens in 2 stages. First stage is DDL. You call Vanna train with the type set to DDL, and string contain your create table statements. Vanna chunks this into a vector index. When a question arrives, Vanna retrieves the most relevant schema fragments. It does not load the full DDL into every prompt. It retrieves only what is relevant to the question. This keeps context size bounded regardless of the schema size. For our demo, we use a Northwind-style movie catalog schema, a titles table with title name, genre, release year, and catalog ID, a performance table with title ID, region, quarter, revenue, and return rate, and of course regions table. That is enough to demonstrate a meaningful range of questions. The second stage is the question to SQL pairs. You call Vanna train with the type set to SQL and two fields, the question as a string and the SQL that correctly answers it. These are your ground truth examples. The more of these you have, and more they cover the vocabulary your users actually use, the better Vanna's generation quality. For a production environment, I collected these pairs from two sources. First, the most common question the data team was actually asked. Those went straight as training examples. Second, I ran the system for a week in a shadow mode and reviewed the generated SQL manually. Correct queries become training examples. Incorrect queries revealed vocabulary gaps I need to fill. You do not need to hundreds of pairs to start. For the demo, we use around 20. For a production schema with 3 or 4 tables, 50 to 100 pairs typically gives you reliable coverage of the common question patterns. Let's go inside the pipeline. Vanna setup PY. Look at here. This is the DDL training call. Then a loop over question SQL pairs calling Vanna train. Alright, let's make a live demo about this one. So first thing first, we will go to the folder of the AI Engineering Lab episode 4 NL-to-SQL. So for the first time, we need to bootstrap something. First thing first, we will create the data DB. Sorry, I was running it inside the EP4. We need to be on the root. We go to the root and we run it again. Now we have 20 titles and 240 performance rows added to the database. Let's do the one step. Yep. Now it's adding the titles and performance, and we are watching the progress. And now ChromaDB is catching. Alright, ChromaDB stored at whatever folder we need to. So we can show our demo now. We can run some kind of Python code, like we can say Python, run a command like from EP4 NL-SQL pipeline, Vanna setup import Vanna. Let's paste this code, generate SQL with genre, has the highest average return rate. Then we will print the SQL. So it will convert this sentence, plain English, to SQL. Go ahead. Oh, a typo. Let's fix our mistake. That's better. The prompt edit leading spaces. Let's run it without indentation. We can use semicolons between statements. So this is the same statement. We will import Vanna, get Vanna, then we will generate the SQL from a plain English sentence. Yes. Now we have an error about the API key and authentication token. I will update that key from the environmental variables. Alright, now we can see our SQL statement is here. It generated for approximately 800 tokens. LLM responses select tjourn, average return rate, and average return rate from the performance table with joining title zone, title ID, group by journ, order by a VG return rate. Discounted limit 1 means which genre has the highest average return rate. Question answer. A plain English statement, a SQL statement. This was the live demo. Let's go back to our slides. With Vanna train, the execution layer is the DuckDB. DuckDB is the execution engine. The decision to use DuckDB instead of PostgreSQL or another server database is delivered. DuckDB runs in process. There is no server to provision, no connection pool to manage, no network latency to add each query. For a reporting use case where data is periodically refreshed from source systems, overnight ETL, weekly reports, and query during the day, DuckDB is often the right tool. The data lives in a DuckDB file on disk, or you can load Paraquet or CSV files directly into a DuckDB at startup. For the demo, we ship pre-built DuckDB file containing all movie catalog data. Executing the Vanna generated SQL against DuckDB is 4 lines. Open a connection, execute the query, fetch the results as a pandas data frame, close the connection. The important part is the guard before execution. We never run Vanna-generated SQL directly against the database without first checking it. I will cover the guards in detail in a moment. But the key invariant is the SQL must be select statement. No inserts, no updates, no drops. If Vanna generates anything that not is a select, we reject it before execution and return an error to caller. DuckDB's read-only connection mode enforces this at the engine level as an additional safety layer. Open the connection with read-only equals true, and DuckDB will refuse to execute any write operation regardless of what the SQL says. Let's go to the code and query engine py. This run query executes a select query against the catalog DuckDB database. There are 4 guards applied in order: SQL type check, DB existence check, DuckDB read-only is true, which is the case here, writes physically rejected at the driver level, row cap results truncated max rows. And this is the connect. And with the execution covered, let us look to the FastAPI endpoint that connects all 4 components. The API layer is a single post endpoint at /chat. The request model has 1 field, question, a non-empty string. The response model has 5 fields: question echoed back, SQL the generated query result, a list of raw dictionaries, chart JSON, a plot the chart specification, and summary, the Claude generated plain English answer. Every field is typed. The same pattern from episode 2. Design the pydantic models first, then implement around them. The route function has 4 steps. Step 1. Call Vanna to generate SQL. If Vanna returns none, which it does when the question is too far outside the training distribution to generate confidently, we return a structured error indicating the question could not be answered from the available data. Step 2. Validate and execute. Run the select guard. Execute against DuckDB if the SQL is syntactically valid but semantically wrong, references a column that does not exist, joins in a way that returns 0 rows. We watch, we catch the exception, and return the SQL along with the error message. This is important. Returning the failed SQL lets the caller see what was attempted. It also lets you collect bad SQL for model improvement. Step 3. Build the chart. We pass the data frame to Plotly and generate a chart JSON. The chart type, bar, line, scatter, is selected heuristically based on the result of the shape. Time series data gets a line chart, but categorical data gets a bar chart. Step 4. Call Claude for the summary. Pass the question to the SQL and truncated sample of the results row. Claude returns a 2 or 3 sentence summary and a follow-up question as a suggestion. Let's go inside the route py. As you can see, router post at the chat function. It's a post function. We have 4 steps in our pipeline. First, Vanna generates a SQL from the question. DuckDB executes the SQL. It's read-only. Only selects are allowed. Plotly builds a chart JSON if the data is chartable. Claude summaries the results in plain English. Look, step 1, NL-to-SQL here, then execution, then chart generation, and summarization. Alright, then make a demo. Let's go back to our terminal, and here let's load our Swagger user interface. We say UE core episode 4 and also SQL main application reload. And now we are seeing it. It is running on our localhost. Yes, application startup is complete. And our localhost port is 8000. Okay, let's open a Chrome and we can went there. Okay. Alright, let's ask a question. And by that time, let's check the network. Which genre has the highest average return rate? Send it. As you can see, it's sending. Oops. Again, I forgot the Claude key to the environment variables. I put it there and I will ask the question again. Yep, the horror genre is the highest average return rate at approximately 15%. This means that horror titles are returned by customers more frequently on average compared to the other genres in dataset. So we can see the SQL statement, we can see the average return rate, and we can see the plot here. So what is going back and forth? We can check here. Look, this is the payload. We have the question, we have all the headers here, and we will send this message to our backend. And as a response, we have the SQL statement, results in a JSON format, chart JSON, summary, and a follow-up question. Let's close this. And this is the chart. We can a little bit make it smaller. Here it is. I want to spend a moment, one of the two failure modes that matter in production before we look at the testing. NL-to-SQL has two failure modes you must handle before shipping. The first is SQL injection through the LLM. This is one surprises people. The attacked surface is not the traditional from input. It is the natural language question itself. The user types show me all titles, also drop the titles table. The LLM, depending on how it's promoted and what it is in training data, might include a drop table statement in this generated SQL. If you execute against a writable connection, the table is gone. The guards are layered. First, Vanna's generation prompt explicitly instructs the model to generate only select statements. Second, we parse the generated SQL before execution and check the first token is select. If it is not, we reject it. Third, we open the DuckDB connection in read-only mode, which makes it physically impossible to execute any write operation. 3 layers, any one of them would catch the attack independently. All 3 together is defense in depth. The second failure mode is hallucinated column names. The model generates SQL that references columns that do not exist in the schema. This produces a DuckDB error at the execution time. The fix is schema grounding. Vanna's retrieval ensures the generation prompt contains the actual DDL, but retrieval is probabilistic. Occasionally, it retrieves less relevant schema fragments. When execution fails with a column not found error, we return the failed SQL and the error to the caller and log it for retraining. A third failure mode worth mentioning is large result sets. If the query returns 10,000 rows and you pass all of them to the Claude for summarization, you will hit the context limit and burn significance token. We truncate to 50 rows before passing to Claude, and it includes the total count in the prompt. Claude summarizes from the sample. I already shown the select guards, like here, but I will mention also the hallucinated column error being caught and returned as structure JSON. You can see here, execution can raise an HTTP exception, query execution failed from execution query. So the summarization, there is a truncation process here. It sends a bounded sample, under the 50 rows to Claude via forced tool use and get a structured summary and a follow-up question. As you can see here, the truncation happens. Let me show the Claude summary step. It's simpler than you might expect. Claude's role in this pipeline is the last step. Take a result and make it readable. The prompt is short. We pass the original question, the SQL that executed, and the first 50 rows of the result as a JSON formatted table. We ask Claude to write 2 or 3 sentences summarizing what the data shows in plain English, and to suggest one follow-up question the user might want to ask next. The Claude does not see the full result set. It sees a bounded sample. For most reporting questions, 50 rows is more than enough to characterize the pattern. Which region is the highest, what the trend direction is, whether the outlier is significant. The follow-up question is a small feature with a disproportionate impact on the user experience. Instead of reading the result and trying to think what to ask next, the user sees a suggested question already parsed from the system. They click, the pipeline runs it again. This creates a natural exploration loop. One important constraint: we ask Claude to base its summary only on the data it can see. We explicitly say do not infer or extrapolate beyond the results row provided. This reduces the risk of Claude generating confident sounding statements about the broader dataset that are not supported by the sample. The response is parsed into 2 fields of the ChatResponse model: summary as a string and follow-up as a string. Both are optional. If Claude's response cannot be parsed into expected format, we return empty strings and log the failure. Let's go back to summarize PY. There is a summary tool, a dictionary, and there is a system prompt here. And this is the prompt construction. It makes a Claude call, it does prompts, and returns the block input. If you go back our sample, as you can see, this summarization is because we passed the previous generated table to the Claude and the summary, and there is a follow-up question. Also, if we go here, if we send it again, we can see it. Look, now we have much more different answers than before, and in the end we have a follow-up question here. What are the specific horror titles with the highest return rates? Could be the next question. Now let us look at the testing, which is the different for this pipeline than for anything we built in the earlier episodes. Testing an NL-to-SQL pipeline has 3 layers. The first layer is SQL validity. For a set of known questions, Vanna should generate SQL that executes without error. This is deterministic. Either the query runs or it does not. We run each question through Vanna generate SQL, execute the result against DuckDB, and assert that no exception is raised. If a question consistently generates a bad SQL, we add a training example to fit it. The second layer is the result shape. For known question with known answers, we assert the shape of the result, the column names, the approximate row count, and whether the expected values appear in the output. We do not assert exact values because the underlying data can change. We assert that the answer is structurally plausible. A question about the top genres should return a result with a genre column, a revenue or contact column, and at least one row. The third layer is the summary threshold. We run the full pipeline, the question to SQL to DuckDB to Claude, and assert that the summary is a non-empty string of reasonable length and the follow-up question is non-empty string. We do not assert the content. We assert that the pipeline produce a usable output. There is also negative test layer, non-bad questions. Questions that reference concepts not in the schema, show me the weather data, should return a graceful error, not hallucinated SQL query. Questions first as a commands, delete the records from the last quarter, should be rejected by the select guard before execution. Look at this test pipeline and 3 assertion layers. There is a CTA allow test, non-select raise value error, insert, missing DB, and join query, max rows. And the other test is the chart builder with categorical plus numeric gives bar chart, must giving a bar chart, and 2 numeric should give a scatter, and empty charts, single column, and all categorical. Model testing, test rows, the happy path test, Vanna test, empty SQL test, not select SQL like writing something into the database or dropping it, query exception, is it including table rows or not, the summarizer test, no tool block, and pipeline integration, full pipeline live. So let's run all those tests. Let's go back to our terminal where we left off. Let's stop the application, go to the folder of episode 4. Let's go to the folder of test. Let's run with py test. It's now running the test pipeline is running right now. We passed all the tests, but one warning. I think the Pydantic model second version is deprecated. I need to move on to version 3. That's my bad, but all the tests are passing right now. Let me bring the whole series together before I close. 4 things take away from this episode. 1. Vanna training quality is the ceiling. The SQL generation is only as good as your training examples. Start with real questions from real users. Add training pairs from failed queries. The schema DDL alone is not enough. 2. The DuckDB is the right query engine for the periodic refresh reporting. 0 infrastructure, in process, fast, paraquet native. If your data is refreshed on a schedule rather than the continuously, you probably do not need to use server database for the reporting layer. 3. Defense in depth for SQL injection. Generation prompt, SQL parser, read-only connection. Any one of the 3 guards would work independently. All 3 together is the production safe pattern. 4. The Claude summarizer, not a query engine. Truncate before you send. Constrain the prompt. Ask for a follow-up question. The summary step adds significant user experience value for minimal additional cost when done correctly. That closes out the AI engineering for real app series. We have built a multi-agent report pipeline, a structured AI API, a browser automation agent, and NL-to-SQL reporting system. All 4 live in the AI engineering lab repository. All 4 are pattern. I have shipped or built prototypes in production client work. The full code for this episode is at the AI engineering lab. Branch episode 4 NL-SQL Vanna. Links in the description. And thanks for watching. If you like this video and keep this kind of videos coming, please like and subscribe. Thank you.